Okay, welcome back. So before I get into the problem that I've started to lay out on the board, I wanted to call attention to a couple of things that I didn't when I was introducing ideal projectile motion. So first off, when we take a look at what's going on with respect to time in the y direction, this was the same sort of situation as we had going on with respect to time for constant acceleration with one-dimensional motion. And that is that we have a quadratic relationship between time and position. This is going to give us a shape of a parabola for our position. We'll go up and we'll go down. It'll change with time and trace out the same basic shape that we have for a parabola. Now, if we play with this a little bit with our equation for what's going on horizontally, we see something else. We also see that if we solve this for time, that time gets to equal the horizontal displacement divided by the x component of velocity, and then time squared then would be that position squared over Vx squared. If we substitute these in to our equation for what's going on vertically, we get delta y is V original y times delta x over Vx minus g over 2 times delta x squared over Vx squared. And so here too, we have a quadratic equation. The delta y is equal to some constant times the change in horizontal position plus some constant times the change in horizontal position squared. And so this too is quadratic, which means that this is also a parabola. The position in space that a projectile, an ideal projectile, will follow will be a parabolic path. We'll note later that when we don't ignore some of those assumptions that we did in the previous video introducing ideal projectile motion, that parabola will change into an ellipse if we have a curved Earth with gravity that points towards the center rather than in parallel directions downward. But over short distances, we get parabolas. Okay, so the problem we've got here that I want to play with to start is this. Let's say that we have a person who's going to run off the end of the diving board and do a cannonball. I've drawn them doing a cannonball. They could be jumping or diving or whatever, but they're going to go straight off horizontally. When I was a kid, my brother and sister and I we were swimmers, but they all drafted us to join the diving team for a bit when they were lower on people. And so the first thing they have you do is get used to the board, and you run off you go off the edge, and one of the positions in diving is tuck position. And that's essentially doing a cannonball if you don't do any flips with it or don't dive coming out of it. So just to get used to the spring of the board. So you can imagine a little kid going off at 6 miles an hour ish. This is like 2.5 meters per second, and want to know, well, okay, you go off the edge. If it's your typical summer outdoor pool, those diving boards are about a meter off the water. So our change in y position is going to be -1 meter over this diver's flight. And so we also want to know, well, how far do they go? What's that horizontal range? We're interested in knowing the time of flight. And we also want to know what's that final speed and angle at the end as well. And so we're going to say, okay, so let's take a look at the problem. We've drawn a diagram. We've started to list our knowns and our unknowns. We can identify from how we've been talking about the problem that this is an ideal projectile motion situation. It's a two-dimensional kinematics problem where these equations are correct relations between our variables. So this is what we get to use. Well, let's see what do we know from the start of this. We know delta y. We know that the original velocity in the y direction is 0. That's known. The time we don't know. The final velocity in the y direction we don't know. And the horizontal range we don't know. Okay, so we take a look at this and we see we've got a couple of questions where there's only a single unknown. So why don't we just go ahead and start from the top there. If we take a look here, we see this equation here. We know everything except for that time. And the time is often the limiting condition for what's going on with projectile motion. So let's take a look. We've got change in y is the original y delta t minus g over 2 delta t squared. And we know, we've specified here, we've made it simple and said, okay, the original velocity in the y direction is 0. Okay, so that makes it pretty straightforward. We want to solve for delta t squared. And so that makes negative g over 2, multiply both sides by that. We get negative 2 over g. Delta y is delta t squared. So delta t is plus or minus the square root of negative 2 delta y over g. Plus or minus here, because you have the solution to taking that square root, the negative square root will yield this equation back as well. We know it's going to be the positive solution for time because we're looking for events that happen after you were at position y0 with vertical velocity of 0 meters per second. Negative time would have been before that, but would also have required that the time before then you had all the same other conditions, like an acceleration of g downward. So the negative time solution doesn't apply here because we weren't accelerating down, we weren't in free fall until time 0. All right, so we're going to get the positive solution here, and so that's square root of negative 2 times negative 1 meter all over about 9.8 meters per second squared. So that's about 1 over 4.9, take the square root of that. So we're looking at something that's a little less than half a second. Let's find out what that is. sorry. I made an error in my estimate. So, right. So, yes, no, 2 over, so, anyway, no, it's about 0.14 seconds. So, 1 over 4.9, around the square root of 1/5. And so that winds up being 0.14 and change seconds. I'm going to leave it at 0.14 for our time. Okay. Now, because we have a limited amount of space on this board, I'm going to put that answer up here. And give us some more workspace. All right. So now that we've found the time, the world is our oyster for finding out our unknowns. We can find our position. We can find the y component of our final velocity. We know that the x component of our final velocity is the same as the x component of our original velocity. It doesn't change because there's no horizontal acceleration for an ideal projectile. So we will find that component and then use trig to find the overall final speed and the angle. But first, let's find the horizontal range. So that's change in position is Vx times change in time. So that's 2.5 meters per second times 0.14. Now I did actually save another couple digits there in my calculator, which is useful to do, or not necessarily in the calculator, but keep those extra significant digits for internal calculations and do the rounding after. And this yields about 0.36 seconds, or sorry, meters. Seconds, meters. So a little bit more than a foot. Not terribly far. Right. That's about 14 inches or thereabouts. So not very far. The scale here is exaggerated horizontally. Okay. How about the velocity? Again, let's go ahead and move that answer up here. To give us some workspace. Okay, so let's find that final velocity in the y direction. Let's see. We could work with either of these two. I'm going to say this one's slightly simpler, so let's run with that. V final y minus the original y, which was 0. Is minus g delta t. Vy final is minus 9.8 times 0.143-ish. So that's about negative 1.4 meters per second. Keep that extra sig fig there, 1.40. And now we have to play with our triangle to figure out the overall speed and the angle. So let's do that. In our triangle, we have Vx is 2.5 meters per second. Vy final is negative 1.4 meters per second. V final then gets to be the square root of 2.5 squared plus 1.4 squared which is about 2.9, 2.87, 2.9 meters per second. But we need that angle to have the full velocity to get the vector. So that angle is the inverse tangent of the y component of velocity over the x component. So that's inverse tan of negative 1.4 over positive 2.5 and that is negative 29 degrees. So we can write our solution for that final velocity, then is the final is 2.9 meters per second at 29 degrees below the horizontal. And there we've got it. Okay, so I'll leave that for there, and we'll do another projectile motion problem in another video.